So yeah, so sorry for that. So I want to talk about timing ultrafast processes and non-adiabaticity. It's quantum battle, so it should be a little bit controversial, I guess. And so I will not talk mainly about tunneling, just a brief primer, also I guess for the battlers afterwards. But we have essentially two wonderful techniques right now to time ultrafast processes. One is the Atto clock, which is essentially elliptical polarization pulses for photoionization, mostly in strong fields. And the other one is, of course, streaking in single photoionization, where you use a very weak linear polarized streaking field. And I will talk mainly about streaking and the problems, or basically whatever we see there. And in both cases, actually, you will see that non-adiabaticity plays a crucial role. And which role that is, I hope to clarify a little bit in this talk. And you see here, my collaborators are, like always, Ulf Salman, who did most of the work for the streaking part I will present. And Jonathan, as a postdoc, joined us recently from Marseille, and Suomi is working towards her PhD thesis on this topic. So this is just a reminder for you what measuring ultra short time spans in photoionization means. So this is really the Atto clock. And the idea is that, this is already from 2008, one might call this a really important paper by now, of course, from the Ursula Keller group, together with collaborators. The idea is when you set an electron free by basically a strong elliptically polarized laser pulse, then through the same strong pulse, this ionized electron is streaked by the rotating vector potential. So its initial momentum when set free is the vector potential at, let's say, an instant of time tau, which is given essentially by the external rotating laser field. And any difference in the angle between this measured momentum in the end at the detector, vectorial momentum that is, and this initial momentum can be interpreted, of course, as a time delay via the relation of the angular difference of the direction of these two momenta divided by the frequency of the laser pulse. Now, of course, in the beginning, we thought this is wonderful to measure ultra short time spans. By now, we are a bit wiser, almost 10 or more years later. So the electron is set free. I deliberately formulated this very loosely. It's set free at the maximum of the laser amplitude. And the time delay is mostly due to tunneling of the electron, if you measure any, for any times t larger than tau. And the green things are really assumptions which are motivated by the adiabatic tunneling picture. That means by a situation where omega is really very, very small. And there's lots of debate about this, and I think you will debate following our three talks even more intensively. And what actually I think has turned out so far, without actually saying what tunneling time is or not, is that certainly the Atto clock electrons are non-adiabatic for 800 nanometer light. And the signature of this non-adiabaticity, I just want to remember you about this or remind you about this, is the energy absorption which occurs under the barrier. I do not say during tunneling through the barrier, deliberately again, I just say under the barrier. And this was our proposal or contribution a couple of years ago. And this was mainly by Hongcheng Ni, who will also be a participant in the battles later on. So I think he will give you more details on that. Therefore, I will be very brief. This can be quantified by so-called classical backpropagation. And in general, the interpretation of timing results, I would say, depend very much on the definition of tunneling. And clearly, tunneling is not a rigorous concept. It's kind of an approximation, since quantum mechanics per se, I would at least claim, does not care about tunneling. It's just quantum mechanics. And tunneling is in a way a semi-classical or even classical concept, which always has its problems. So let's have a quick look on this backpropagation. This is shown here. So we basically solve the time-dependent Schrödinger equation for normal tunneling or whatever strong field problem. That means we have a helium atom, one active electron in its ground state. We solve the time-dependent Schrödinger equation quantum mechanically. in this elliptically, or for us, it's easier in theory, circularly polarized laser field. You see it's a pulse, I think 2 or 4 cycles. And what we do then, once we have propagated for quite some time, we can kind of isolate the ionized fraction far out of the wave packet, far out from the nucleus. And then we convert this basically to a classical probability distribution, and taking this into trajectories by taking the momentum as the gradient of the phase of the wave function of the ionized part, and basically the density for the rest. And then we propagate these trajectories backwards towards the nucleus. So we kind of undo the ionization, if you wish. And now comes your favorite tunneling condition. You can use this to implement any tunneling condition you like. We think the most, how to say, general one is probably to require that at least one momentum component of your tunneling or tunneled wave packet goes through 0 at the tunnel exit. How would you otherwise distinguish that something is tunneling or not? So this is what we do. We kind of stop the wave packet at the closest position where the instant momentum, or the momentum in the instant direction of the laser field, has a 0. And when we do this, we kind of retrieve all the things we discussed before. And you see this here in a quick movie. This was made by Hong Cheng for quite a while ago. You see this is circularly polarized laser pulse, a 2-cycle pulse, 800 nanometers, intensity 8 × 10⁻⁴ watt per square centimeter, and as I said, helium single active electron. And this is now shown here, the time evolution of the helium density. Going out, it's just the quantum density. Going back, it's the classical ionized part. Let's see what happens if you see something. So nothing in the beginning, the time is running on top. 0 is the maximum amplitude. Now you see it's going out. And this is classical back propagation. So it's really going nicely back again. And you see in the end it's hollow. Why? Because we took out basically the bound states. So that's only the ionized part coming back. And just to tell you in a nutshell, since I want to emphasize non-adiabaticity, what really happens, you see here in the bottom on the right-hand side, this is the energy we can monitor at this tunnel exit. And you see the energy of the tunnel exit, it's just the average energy of this ionized wave packet. It only agrees with our assumption of adiabatic tunneling. That means nothing changed from the ground state electron, and especially its energy, which is minus 0.9 eV for helium, only for high intensities. Or if you formulate this in terms of a Keldysh parameter, for small Keldysh parameter, or if you wish, in the limit of vanishing frequency. Of course, we varied here the intensity, not the frequency. Varying the frequency is not so easy in theory, and probably also not experiment. So this tells you that non-adiabaticity is an element, a key element in this Attoscience process. And our expectation we have probably, or our intuition, is only met in the adiabatic situation, which is not really achieved in the range of intensities or parameters we kind of use the Attoscience clock. And of course, we can't use the Attoscience clock in this limit for very high intensity, because then you have over-barrier ionization, and this doesn't work. So this limit is not reachable for the Attoscience clock setup, where really adiabaticity is reached. Now you can see this was published, the first publication in 2016 by us, and I think there's another more extensive one in 2018, and Hong Cheng has, I think, new interesting stuff he probably will tell you about, Hong Cheng Ni. And there's recent reviews about this, just fresh from the press, so to speak, by Anoti Kaifetz, a topical review this year, and last year Cornelia, who is also a participant in the battles later on, published a review in 2019. And I guess they don't really come to the same conclusion, but that's why it's interesting. So let me continue and come basically to the stuff I really wanted to talk about. This is streaking of single photoionization. Now streaking is again another way to start and stop the clock. So you start the clock by initiate the ionization with an XUV Atto pulse, and you stop the clock in a way by timing the ionization with an IR streaking in the time domain or in the frequency domain with rabbit, with the frequency cone. So the IR field here is very, very weak. It's just really a probe. And the process you want to look at is single photoionization with an XUV pulse and a pulse, because you want to start the clock for photoionization. And of course, the elegant experiment is that both of them are phase locked because they are generated by the same original strong IR field, the Atto pulse as well as the streaking pulse. Here are all the papers of the initial kind of ideas and publications. So that's the setup again. You have photoionization, very simple, without any streaking field. That's what we know. Initial state, bound state with a photon frequency omega. That's the central frequency also of the Atto pulse later, above the threshold, and you end up somewhere in the continuum. And this continuum energy, I will call excess energy E in the following, is given by initial energy plus photon energy. Now the streaking idea is that you kind of modulate the energy of the electron where it actually goes to the state in the continuum by a weak streaking pulse here. And that means you put basically a timestamp here on this evolution. So if you come later, you will end up with a different energy in the continuum. That's the whole idea of the streaking. And this gives you then different final electron momenta. You see them here. This is the streaking momentum. It's just basically the interval of the field strength until infinity from the time where it was streaked. And now you can, of course, monitor this and record this as a function of the time delay. And typical parameters in the beginning were 100 EV, XUV photon frequency, 200 attosecond pulse. So this is a streaking spectrogram, and of course you cannot measure absolute delays in that way, but you can measure elegantly relative delays, because with the same laser pulse you ionize two different orbitals, let's say in neon, then they have two different excess energies, and you can extract the relative delay for photoelectrons which come from the 2p and the 2s orbital. And this was found in the original experiment to be something like 20 attoseconds. And I think it's still not really reproduced. Maybe it is by now. I have not completely followed the literature. And the question is, that's a clean measurement. What does this delay between these two streaking kind of shifts, what does this really mean? Now, I want to kind of discuss this in the context, of course, of Wigner time delay, because this is the concept theoreticians came up very early with to relate it to. Wigner time delay is an old concept from collision theory. It's related to the scattering matrix, here written in the angular momentum basis for conserved angular momenta, which is the case for an electron which comes from a well-defined bound angular momentum and is photonized by a single electron. And then the Wigner time delay is essentially the derivative, the energy derivative of the energy-dependent phase shift. And since photoionization is a half collision, you expect half this time delay. So photoionization time delay is the energy derivative of the phase of the dipole matrix element. Now, is this really the time determined in the photoionization streaking experiments? So this was never really proven. It was shown that it is similar in certain situations, especially for short-range potentials like Yukawa, but it was not really derived from the physical process of a streaked electron momentum. And this is what's measured in the experiment, streaked photoelectron momenta. So what I want to tell you now is an investigation where we really determine the photoelectron momenta directly from energy absorption. And we do this to be transparent in the simplest possible approach, just for proof of principle. That is, we do it classically and we do it in one dimension. Now let's see, first of all, what is the classical Wigner time delay? This is actually very simple. You start propagating your electron trajectory somewhere at the origin in the potential with the final excess energy. So photoionization or absorption has taken place on the final energy surface, now without streaking laser pulse, just pure energy conserving system. And then the time delay is given by the derivative of the action with respect to energy, and that is the relative action of the photoelectron coming out under the action of the potential and the particle electron coming out without potential. That's the idea of the time delay, the Wigner time delay. You kind of compare the time it takes a particle to come out from a potential compared to a free particle of the same final energy. And of course, now you can calculate this. It takes this form as an integral over r. You see it's the momentum action for those of you who know this, or what's also called the collisional action. And you can convert this, and this is very important, changing the integration variable to a time integral. This brings us closer to the streaking scenario already. And you see P of r is the momentum, including the potential. P sub e is just the free momentum, or also here the asymptotic momentum once the potential is gone. So that's the form. And that means the Wigner time delay is defined through the asymptotic momentum difference of free particle and particle in potential. And here you see the comparison, though this is the Wigner time delay, and this is what we look ahead now for. This is times an attosecond, and this is essentially here the electron excess energy. And you see these are already streaking time shifts, and I will tell you in a second how we calculate them. And this is shown here for a Yukawa potential. And you see already, so it actually, the streaking kind of shifts approach the Wigner time delay, but only in certain limits. So they approach the Wigner time delay if the wavelength is really long, longer and longer, or /n if the electron excess energy is high, but not in general. And this is done here for a Yukawa potential with a screening length of 3 angstrom, just for your reference. So let's see how we can rationalize that. And here's, here's already the first clue. So we write this again in a different form. We write it basically by partial integration as an integral over time, including the potential. And here you see now, this is the derivative of the potential which enters here. And this is kind of an average of time already. So let's come now really to the momentum, the streak momentum, how it can be derived. I should emphasize that all the figures you see are electron momenta calculated numerically without approximation. This is just solution of the full classical equations. But of course, in accordance with the streaking scenario, we are always in a limit where our streaking field, the vector potential of it, over the energy of the photoelectron or its momentum is small, roughly 1%. And what facilitates the understanding, the derivation, is that an analytical expression for the momentum change can be given very easily in a closed form if we assume that the potential is weak. So this is basically the limit in the weak kind of streaking potential, streaking field. Then you see this momentum change is given by this expression, or can be written like this. And you probably recognize very easily what is traditionally done in strong field approximation. There is no potential. And then the streaking shift is simply given by the imprint of the vector potential in the beginning where the electron appears in the continuum. But of course, this should be modified through the potential. And that's what we want to calculate. Now I can write this, now I can parameterize, I would say, my streaking momentum shift simply for harmonic fields in a harmonic basis. This is done here. This is nothing but a reparameterization. And then the streaking shift would be given by the arctant of these two components here. And the nice thing is now, if you parameterize this expression in this way, then you see this component is basically given by that expression involving the derivative of the potential. And you see this is already very close to what we want. But before I come to that, let's see how we read off our streaking kind of time shifts. We simply take the computed, and now this is numerically computed streaked electron momentum, the gray dots here, and fit it to a harmonic, a sinusoidal kind of function, which represents more or less our streaking driving field. And then, of course, we can read off the shift, the time shift, very easily. And you see, for doing this, you need not a special basically delay S to do this. Of course, it gets better if you get through the whole period of the streaking delays, but you can do this at any kind of point S. So without any restriction, we can take S to 0, and then we see the following. So at S equals 0, the streaking shift is given by this expression, and it looks like this one here, quite directly. So it's given basically with high C, because high S doesn't play a role since its harmonic component is 0 at s equals 0. Now, remember that the Wigner time delay is given by this expression. And now you see where it comes from or where the relation and connection is. So this expression, of course, if omega is small, gives exactly t. Sine omega t over omega gives t. And then you have a direct relation between the streaking shift and the Wigner time delay. So more precisely, in the limit, in the adiabatic limit, you recognize it again, omega to 0, the streaking time shift agrees with the Wigner time delay for a Yukawa potential. This is what we have derived this for. Now you see here a calculation, and miraculously it also gives you a finite result very nicely, almost similarly for the Coulomb potential. But this is now a contradiction. This should not be, right? Because we know that the Wigner time delay basically does not converge for long-range potential. And here's a resolution, at least for the time being. The streaking shift agrees with the Wigner time delay only in the adiabatic limit, omega to 0. And additionally, you need, and this is the adiabaticity condition reformulated because, of course, it's not absolute in omega, it's always relative to another energy scale, that essentially the electron, the photoelectron, should leave the range of the potential in a quarter of a period of the streaking field. So this expression should be much rather larger than RV. And RV is the range of the potential. And this now explains also what I showed you before. Of course, you get kind of good agreement for a low, small omega, large wavelengths, but also you get it for high excess energy. This, of course, helps to leave kind of the potential fast. And now comes already kind of where the problem lies for Coulomb. You know, Coulomb has infinite range, so you never really leave the potential. So this adiabaticity condition is never fulfilled for a pure Coulomb problem. And the point is, and we come to this in a second, that the energy absorption kind of really gives you a wrong impression. Of course, what streaking does, it always leads to a finite energy absorption. Since energy is absorbed, you see this here only basically in 1/4 of the streaking period. You see here, this is a strong positive amplitude, strong negative amplitude of the laser field. This is the absorbed energy at different wavelengths. This is for Yukawa, the lower one is for Coulomb. And you see this kind of settles on a certain value roughly after a quarter of the period. If you change your wavelengths, make it lower, you absorb more, but for Yukawa, this eventually saturates and gives you the limit of the Wigner time delay, what you can extract from this energy absorption. Now for Coulomb, and this is in accordance with the fact that the Coulomb potential has infinite range, this energy absorption never settles. You can make the wavelengths longer and longer. You cut out basically a larger and larger part of the potential where you interact with and still have energy absorption. You get larger and larger energy absorption. So this means that the streaking shifts for the Coulomb potential are finite for the wrong reason, because the streaking terminates energy absorption after a quarter of the period. And for streaking shifts to resemble a clean system property, which is independent of the properties of your probe field, the streaking field, or the excess energy, the photon electrons really must have left the range of the potential after a quarter of the streaking period. This is impossible for pure Coulomb. And this is almost the last thing I tell you as an overview, the streaking shifts. So this summarizes what I just said. These are the streaking shifts as a function of wavelengths for a certain excess energy, 10 eV. You see the Yukawa potential, and you see if you make the wavelengths longer, that's what we discussed, get a very nice limit. And you see the arrows are really the converged values, which is here for wavelengths of 100 micrometers. So this is really where it's adiabatic, you get a nice converged limit. It agrees with the Wigner time delay. Now for Coulomb, you see this increases, the streaking shifts, they increase and increase. There's no chance for get convergence. Now, if you do the same thing now for basically two different energies, you see the dilemma that even that doesn't help, because absolutely speaking, the streaking shift for Coulomb potential really depends also on the excess energy. So at 10 eV, you get this excess energy. At 30, you get this one. The difference gives you the black line. Also, this one doesn't converge. So it gives you, of course, a finite value, but it's not necessarily what you should associate with a clean system property. The only way to achieve this is basically if you kind of gauge your Coulombic potential, which has a Coulomb tail. That's a realistic thing. You never have pure Coulomb systems, only hydrogen is that. If you kind of reference your Coulombic tail, instead of the free particle, as it is for the Wigner time delay, with the Coulomb particle, that is a pure Coulomb potential. That's the reference here. If you do this in the same spirit as for the Wigner time delay, take the difference in the momenta, then you actually get a converged value. And this is what we would probably propose. And you see here, the Coulomb potential is, the Coulombic one is just mimicked as a soft core with a finite soft core parameter of 3 angstrom here. So the streaking shift for potentials with Coulomb tail must be referenced with pure Coulomb potential shift for adiabatic convergence. Then you get a limit which is independent, basically, of your properties of the probing pulse. And that's very important, comparing shifts of 2 orbitals. What was done originally, and this seems to be very elegant, of course, in the experiment, with the same laser does not help, because this is exactly this situation. You have different excess energies, and that also does not converge. So that's a summary. Adiabaticity is the key condition which ultrafast timing techniques need to do what they should do. And non-adiabaticity is very interesting for theoreticians, but it's not really very helpful if you want to use this as a passive technique for bringing out properties of your target system. And in particular for streaking and photoionization, adiabaticity lets streaking shifts converge to Wigner delay for short-range potentials. And streaking shifts for Coulomb potentials are finite for the wrong reason. They should be measured relative to reference system, Coulomb reference system, at the same excess energy. And as I said, in the end, traditional relative streaking shifts of 2 ionized orbitals with a different binding energy with the same light pulse, this does not really help because they have different excess energy. So I'm done. Thanks for your attention.
So yeah, Michel, thanks for the nice talk. Are there questions, comments? Please type the questions in the QA box for those who are attending. And the first question is from Heiner Donna. Can you comment on timing of multiphoton transitions?
We have not done this explicitly, but of course, multiphoton transitions are in general in the very kind of, how to say, non-adiabatic limit, if you think of the Keldysh parameter. So I would expect they're really a different kind of physics.
Thanks a lot. I also have one question, because I was seeing that you were defining adiabaticity, and some people would say that you not necessarily have to have a constant energy, but you have to have some energy that is gradually changing and adapting to your external conditions. I know this is a question of definition, and we are talking here about metals, so many people would agree on some concept and some people would disagree on the concept. But if you look at the definition, for instance, by Born and Fock, what they say is that you can, for an adiabatic system, define an instantaneous eigenstate that should change. So naively speaking, if you think about it, for instance, you have an effective potential that is changing over time, which is composed by the field and whatever barrier you have. Could you not say this is adiabatic?
So I think you're right. In general, adiabaticity, what adiabaticity is concerned, I mean, in the context of time shifts and streaking, it's very clear, I think, and I make clear what adiabaticity I have in mind. So what I think we need is that our measuring apparatus does not kind of change the thing we want to measure. Otherwise, it's not what we normally call a measurement. we can still do this, and of course all the measurements are correct, but the interpretation normally relies on this assumed concept of adiabatic change, or something has not really changed in terms of properties of the target. And I tried to convey that this is for standard setups of basically our ultra short timing concepts, autoclock as well as streaking. This is not necessarily given. So in the streaking context, this is actually mostly fulfilled for 800 nanometers and for the target systems we use. Yet you see, it's very tricky because, as you say, it's not absolute with the frequency, it's always relative. I mean, it needs to be small compared to another energy, right? That's the excess energy of the electron. That's kind of the internal time scale of your potential, the asymptotic excess energy of the photoelectron. And also, and this is kind of surprising, basically the timing, the streaking time shift really depends on this excess energy. Therefore, this kind of natural and not naive, it's, I think, very clever of comparing two orbitals, right, being ionized by the same laser does not help. This does not give a converged value which is independent of your properties of the streaking field. So therefore, one needs really to think how adiabaticity figures in which aspect.
Yeah, thank you. I think it's a key question because a lot of people, they talk about adiabaticity and you see that the concept is oversimplified many times. And I think this is a key issue. We also have here a question from Henjit. And they're asking, could you please tell me which method are you using for wave packet propagation?
So we use here purely classical wave packet propagation because it's photoionization, we are high above the threshold. And so there's nothing to worry about tunneling or something like this. And yeah, it's classical, basically molecular dynamics, if you wish. And it's actually sufficient to extract the timing, it's sufficient to take the lead or the characteristic trajectory, which is the maximum of your Gaussian or whatever distribution of a wave packet. So taking the full wave packet, you can do this. We also did this. This only kind of reduces the contrast in your signals you measure, but it gives you the same result.
Thank you. Andrew Brown would like also to talk about this question. So Andrew, you wanted to refer to the previous question. Can you please unmute yourself?
I don't have another question, just there's several questions still in the Q&A to be answered there.
Yes, okay. So from Camilo Ruiz Mendes, he would like to know what about measuring stereo Wigner time delays, which means using the same final excess energy. Is that better than using two orbitals?
Yeah, I mean, measuring the same final excess energy is definitely okay. This is what comes out from this analysis. So that makes a valid reference in a way, yeah.
So Jens Bigert would also like to know, when going to ever longer wavelengths, the magnetic field component gets more prominent. How about that component for the timing momentum changes? Yeah, we know this is a real issue, so we would like to know.
Very good question. We will tackle this in the future.
Okay, very good. So now we have a raised hand. Let me have a look.
And I could just answer one more question, which comes as next in the chat. Of course, we are working right now on Rabbit. This will be the quantum version in general, and this should also then, of course, we expect the same kind of conclusion to apply also to the Rabbit technique of streaking when we're working on this, and this is, of course, the quantum version, which needs interference.
Okay, so there is a raised hand. Henry, you are hosting. Can you allow the raised hand, please, to speak? Where is it?
I'm trying to find who it is who's raised their hand.
Yeah, because we have a lot of people and we have one raised hand.
What's the participant's name?
I don't know, someone raised the hand. I think we're okay with the questions in the QA box, but there was one raised hand, and
so while you're trying to find the raised hand, I can try to answer the next question in the box, which says, how does the adiabaticity play a role in non-Coulombic, non-spherical potential, where an angle plays a role in the photoionization? And this would not matter. I think this can be done in the very same way, because you can essentially formulate everything not in terms of partial waves for conserved angular momentum, time delay, but just basically as a vector and then scalar product for the time delay of the PDR, the action. So the action is a scalar, and it doesn't matter if the angular momentum is conserved or not, and this is all you need.